Hi, my name's Byron, and you're at the Macquarie University School of Engineering Waterloo facility. Here we conduct research, do project-based learning, and host student groups. One of those student groups is NQ Speed, and their objective is to set the land speed record for human-powered vehicles. They've kindly joined us today to walk through one of their issues and the engineering that they used to solve it. As we explore the problem, feel free to look around and explore the facility. Engineering at its core is about problem solving, which often involves tasks in minimizing, maximizing, or optimizing. But before we can get to solving that problem, we need to know more about the problem. Here we're joined by Mike Simmons, who will explain the problem to us.
The problem we observed with our first bike, Mach 1, was the twisting of the chain as we got into higher gears. As you can see here, we ran a traditional bicycle shifting mechanism, which pushed the chain across, causing a misalignment between the front and back sprockets. This cross-chaining induced friction, which ended up reducing our top speed.
Great. Let's join the other team members and work through the problem.
So the team has come up with multiple solutions to the problem. What have you guys narrowed it down to?
So we started by looking at the drivetrain. Here are some alternate concepts we came up with, including the CVT, which is a continuously variable transmission, often found in cars. This isn't often implemented in bicycles, and we think this is an innovative step. We also looked at the hub gear design and translational cassette, and we think the translational cassette is the most preferable as it reduces cross-training to improve the overall efficiency of the system. James has an idea on how to implement this into the bike.
In mechatronics, we deal with these problems a lot. We can use a stepper motor to drive a lead screw to move the cassette, but I will need your help to mount the stepper motor in order to keep the assembly stiff.
In modern engineering, we come across these multidisciplinary problems all the time as the solutions become more and more complex. Let's head over to the CAD Lab to see Matt and see how the detailed design is coming along.
Computer-aided design is a crucial skill for engineers to learn, as it allows for the virtual testing of many designs and trialing of concepts before committing to making a part. We don't want to be trialing error bridge, for example. That would make for a very big cleanup. Here, Matt's been working on the mounting hardware for the computer-controlled cassette, while James has been developing the electronics and code. How's it coming along, Matt?
The team has been using computer-aided design since the beginning of the project. So we have a digital twin of the bike in the workshop, and every part we start here, perform a number of simulations. We check the clearance and are able to find the strength and the weight of the components. We are confident that this will work. However, we do need to check with our machinist before we can commit to the design.
We're now in School Workshop, where students interact with qualified trades and technical tutors to build parts and fit into the bike. I'm joined here by Noor, one of those technical tutors and a student here at Macquarie, to walk us through how fabrication fits into the engineering process.
As engineering students design solutions to a problem, they quickly get to a point where they can't make their own part and they need to hand over the manufacturing to a qualified trade. This communication and interaction between engineering professionals and engineering trades is crucial to get right. For these student teams, parts are quite straightforward to make, and with some patience and training, the students can make the parts themselves, which provides an invaluable experience.
Thanks. Once the part's made, the job isn't done. We need to fit it to the bike and test to make sure that the solution has solved the problem. But does it work? The team has put a lot of effort in to get to this stage. And the last step in our engineering process is testing. Mike, can you take us through some of the tests the team has done?
Absolutely. Going for the record is a really high stakes moment, so we want to do as much testing as possible to minimize the risk of failure at the last moment. We test our manufacturing processes, as well as our aerodynamics with both CFD simulations on the computer and wind tunnel testing. We also test our mechanical components on test rigs like this one. Our solution to the problem is compact, stiff, and the gear changes are quick. We're really happy with it at the moment, but we want to make some modifications to ensure its reliability when we go for the final record.
Thanks, Mike. And thanks for joining us and learning a little bit more about engineering and what it takes to go from an idea to execution.